Hello, welcome to another Coding Train coding challenge. And in this challenge, whoa, this train is really loud. Can you please pull out of the station now? On the train are roses. Because one thing that I really like are flowers. And there's some wonderful mathematical algorithms that you can get to make these beautiful rose like patterns, and you can see even here all sorts of different possibilities. So I've been really interested in tiling and symmetry, and I'm hoping to do many more videos about different topics like that, and this is kind of along those lines. So this is actually something that I could do with just this incredibly simple formula where r equals cosine of k times theta. So what does that formula mean? We're going to have to figure that out first. So, oh, wrong button. Over here for a second. So here's the thing. The stuff that I'm going to code, which I have not done before, so hopefully it's going to work, is built entirely around this idea of polar coordinates. So if I have a Cartesian space, meaning a plane, a flat plane like this whiteboard, not a plane flying in the air, a plane like this whiteboard, and I have a point in the plane, you know, this is the same as I might have a point in a canvas. In all my videos and in computer graphics and in programming, we usually think of this point as an XY location. But actually, right, this is its X location, and this is its Y location. But another way, and this is known as a Cartesian coordinate, named for the French mathematician René Descartes. Okay, now how did I do, French viewers? Now, I just sounded like a completely ridiculous person. Now, you could also think of this point as a distance from the center known as r, radius or distance from the center, and an angle relative to the x-axis. This r comma theta is known as a polar coordinate. So here's the thing. Remember, you know those functions sine and cosine? So, ka, toa. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Here's our triangle. Here's this angle. So sine of the angle equals opposite, or y, divided by hypotenuse, or r. Cosine of the angle equals, x divided adjacent, which is x, over hypotenuse, which is r. I could write these in another way and say y equals r times sine of theta, and x equals r times cosine of theta. In other words, camera's over here, but I think you can still see me. In other words, I can think, my mind can think in terms of polar coordinates. I can calculate r's and calculate thetas and do all sorts of stuff. And yet I can draw something P5, or processing, whichever environment that I would use, only accepts in the ellipse function, and the point function, the vertex function, Cartesian coordinates. So this is a way of me converting from polar, which I'm going to think in, to Cartesian. So let's come back, and that's actually what I want to do here, is this idea is use this formula as a way of calculating a radius based on an angle. The radius, how far from the center, is going to be cosine times k some constant, and then this formula here is if this is r, x equals r times cosine of theta, y equals r times sine of theta. So we should be able to do this relatively quickly. I kind of wish that I was doing this in processing for some reason, but I'm doing it in P5. I'll make a processing version and post a link to that code in the description as well. Okay, so let's just say, for the sake of argument, that I'm going to write a loop, because I think this is probably the easiest way to do it for the moment. And I'm going to write a loop where I can't write 2 pi, where I have a variable called a, which starts at 0, goes all the way up to 2 pi, and I don't know, I'm going to increment by some arbitrary amount. I could be more thoughtful about how I do this. And so now, just to see that this works, I'm going to say var x equals, let's make up an r. Var r equals 100. Var x equals r times cosine of that angle. Var y equals r times sine of that angle. And now let's just draw a point. Stroke 255, where did that console.log come from? Stroke weight 4, and then point x comma y. Now here's the thing. This is all predicated on the notion of having these points around the point of origin. But the point of origin by default on the canvas is the top left. So actually, before I do any of this, I want to use translate to put that origin in the center. The top of this marker went down over here. I'm back. Okay, so now what I want to do is add translate to the center, which is width divided by 2, height divided by 2. And then let's see what we get. There we go. So you can see, look, I got a circle. So something's working correctly here. And you can see here if I say go up by 0.1, we can see, I'm drawing all these little points. This is just a simple demonstration of polar to Cartesian transformation. But now, let's go back and let's go back to that Wikipedia page and let's try k equals 7. Let's try k equals 7. So r equals cosine of k times theta, or the angle, that is. My variable is a. So r equals cosine of 7 times a. Now let's try this. Hey, what happened there? So I wonder if I need to really expand things out, or I just need to quit. There we go. So I just need to expand things out. Now, what I might want to do now is have a bit more gradation. And so I could start to see this pattern forming. And what I can actually do that would make more sense now is for me to say begin shape, end shape. Forget about the stroke weight, or just make the stroke weight 1 and set these as vertices. So what this does, instead of drawing a dot at every spot, I'm saying begin a shape, end a shape, and connect everything. And then maybe at the end I'm going to say close. And we can see, there we go. Look at my beautiful rose pattern. So in a way, we're done. That was like the quickest coding challenge with no editing whatsoever. That never happens. But let's make this worse. I should just quit while I'm ahead. It's like, that was like 8 minutes or something. Less than that even. Let's see what we can do. So let's just try some of these other, let's try k equals 4. And I should probably make this, let's make this a kind of global variable for right now. I'll just put it here in draw. K. Actually, what I really should do is make that something that I adjust with a slider. Oh my goodness, that's crazy. So let me say k equals 4 and change this to k. Whoops, in the wrong place. We can see, there we go, with k equals 4. Okay, let's try some of these patterns. So for example, I like this one, which is like 5 with k equal, you can see this, k equals n divided by d. And this is a table, 5 divided by 6, or 5 divided by 8. Let's try one of those. So let me come back into the code and add a variable called k, and actually just put k down here. And then what I can do is, so this should be the same, 4. One thing I want to do is get rid of the fill, just so I can see it like this. And then what I want to do, whoops, is change this to, what did I say it was? 5 divided by 8. Okay, so this I think is right. And I had a problem with this. And I think the issue is that I need to now go around the loop multiple times. So I wonder if there's a way to calculate that exactly, but I'm just going to multiply this by 10. And we can see, there we go. So if I go around the loop multiple times, we get this beautiful, nice tiling pattern. Maybe I went too many times. I'm not sure what this extra line is doing here. It's like connecting back to the center. So I'm sure I could clean this up in some ways. But I think what would be interesting to see right now, very quickly, is if I add the DOM library, and if I say var slider, slider equals create slider, and let's give a range between 1 and 10, starting with 4, and increment rate of 0.1. What I should see is now I can say k equals slider.value. Now let's give this a try. So now as I change the slider, we can sort of see different possible shapes and possibilities as I move it around. So anyway, so I think there's probably a precise way you could calculate you could calculate how many loops you need. Alka in the chat suggests, actually, like looking at this, that you need, depending on what this d value is, the denominator of this frac, that's how many times you need to go around the loop, which makes a lot of sense actually. because how you're multiplying by pi, you don't need to hit all the sort of angles to get all the positions. But anyway, so we could sort of test that. I'm going to take the slider out just for a second and say multiply by the denominator value. And we can see, yeah, there we go. Now that's perfect. So that's definitely right that you need d loops. And so we could change this to be, oh, this is exciting. Because what we could do actually have two sliders. We could say d, the denominator is 8. The numerator is 5. And I could say slider d, slider n. Slider d equals some value between 0, 1, and 10, starting at 5. And slider n, some value between 1 and 10, starting at 5. And then I could say here, d equals slider d's value, n equals slider n value. And I could say k equals d, no, numerator divided by denominator. And then I could keep d right here, and k is here. And I think now we would have, yeah, you can see here the different types of patterns I'm getting, which I think are correct and probably match. Now, it would be nice for me to report. It would be nice for me to actually report what those values are and then double check them. But I think this is Rose mathematics pedal stuff. So how can you maybe, play with this, create a whole bunch of them, have it morph from one to the other, fill it with colors, tile them all next in a pattern. I'm sure there are a lot of possibilities. Yeah, I should probably make the step size smaller, which would also give me maybe a more fluid. Alka in the chat is giving me lots of great suggestions. Give me a more fluid view of this. And we can see, oh, look at this. Ooh, we're going to get some weird funny business here for strange decimal numbers. But you can sort of see one, and I have to clean up this thing where it doesn't end back at the beginning. So anyway, so there are a lot of wonderful possibilities here. I hope you enjoyed this Rose Mathematics Challenge. I hope you make some stuff with it, share it with me, and I would love to see the world filled with flowers. That's what my dream is, or at least computational flowers. So make some GIFs, make some images, tweet them, share them with the @Schiffman, and I'll see you. And the next train is leaving the station.